When I was a PhD student, I was doing experiments on laminar jet diffusion flames. So we would take acetylene or butadiene, very sooty fuels, and burn them on just round tubes and measure as much as we could about the soot formation. And for a combustion scientist, this is kind of a dream experiment because you turn the knob and the flame gets shorter, turn the knob, the flame gets longer, and you measure the flow rate. You really control the fuel consumption rate, which is the burning rate, and the heat release rate. In a lot of fire studies, it's not like that because you're working either with liquids or with solids, and the story gets a lot more complicated. So for the next 2 hours, I'm going to start talking about burning some gases on a standard test called the cup burner, but then transition to burning liquids. You can see a little bit about how liquids burn, and finally to solids in the next hour. I think for almost all combustion scientists, you either want to burn gases where you have nice control over the concentrations and the flow rates, or if you're burning liquids, like in a gasoline or a diesel engine, you try to either have all the liquid evaporate, in the case of gasoline, or if you've got diesel or jet fuel, to have such a fine spray that it's almost, they call it atomized, and very small liquid droplets. And similarly, if you're burning coal in a coal power plant, try to make those coal particles large. But in fire research, you can't really control the size. Having wood the size of dust wouldn't be very nice for the tables in this room. So with that, let's get to these standard tests. So these are 2 standard tests that we have in our laboratory. If any of you ever is near University of Maryland, just outside the Beltway, no, just outside of DC, within the Beltway, please let me know. I'll show you these tests. They're fascinating, wonderful little standards. They're called standards because they're covered by ASTM, American Standard of Testing and Materials. And so anybody else who performs one of these standard tests should get exactly the same results. And I want to acknowledge the people who helped me prepare to teach this material. All of our undergraduates actually perform these tests in their senior lab class. And that's Andre Marshall, Jim Quinteri, and Stas Stoliarov from my department. So this is the cup burner. This is a sketch right out of the standard that shows what the cup burner looks like. And everything here is made out of transparent glass or other ceramics. So there's a chimney, and inside that, the cup. So what you do is you flow into the chimney air. You start flowing air, and then into the cup with the separate valve, and it's nice you have these 2 valves to start with. You turn on your fuel, and you snake just a butane lighter, barbecue lighter in there, and you ignite a flame. And so now you get a teardrop-shaped flame burning on top of this cup. And then you slowly add some extinguishing agent, for example, carbon dioxide is very effective, into the air until the flame extinguishes. And the cup burner is all about measuring the point of extinguishment. At what concentration of agent can you actually extinguish your flame? So I'm going to talk about how it works with gases. We do it with methane, propane, usually methane or propane or ethane in our lab, but it can also be done with liquids. If you want to do it with heptane, then you need to have some way of adjusting the temperature of the cup, cooling it with cooling water, because with heptane, you have no good way to control the flow rate. So you have to control the flow rate with the temperature. So on the next slide, I'll show some of the dimensions of the burner. So the cup has an inside diameter of 26 millimeters, OD of 31, and the chimney is 85 millimeters. So these are all small items that you can pick up with your hands. They're a little bit fragile, and those glass materials are rather costly because they're made out of quartz. So you could use normal window glass, borosilicate glass, but this has a high coefficient of thermal expansion. Anybody who's ever tried to bake in a regular plate, you put a ceramic plate in the oven, as it heats up, it expands, and usually you'll break the plate. But things like Pyrex and quartz, if you put them in the oven, they're okay. This is almost like an oven. The cup gets very hot, and the chimney also can get quite hot. And this is an NFPA standard, actually, from 2018. Okay, so that's the cup burner, and those are the dimensions. So this is how the flow rates work when you do a cup burner test. So Initially, you start your fuel flow rate, methane, propane, sometimes heptane, and that's this Q fuel at the bottom left that goes into the cup. As I mentioned, you turn on then your flow rate of air, goes into these glass beads, so you have a nice uniform top hat velocity profile. And after a few seconds, when you feel like your flow rates are steady, you ignite the flame and start to flow your agent. That's at the bottom right of the screen. And typically your agent could be nitrogen, CO2, sometimes use halon or water mist and other agents. A colleague of mine at NIST, Greg Lanteris, he's done a lot of these tests using halon and other halogens. And he always complains that you put that halon in there, it suppresses the flame at a very low concentration, but just like we saw yesterday with refrigerant fires, it etches the glass. You make a lot of HF and it etches the glass. You also make Teflon when it burns, these PFAS. And so you get this kind of plastic polymerized Teflon on the inside of your chimney. And it's hard to clean it. And certainly if it etches, you need to replace the chimney. So this is a procedure. You set the airflow rate to 40 liters per minute, turn on your fuel and ignite it, and then you adjust the flame length to around 80 millimeters long, and then slowly increase the flow rate of the agent until it extinguishes. And again, you see a lot of interesting phenomena as it approaches this extinguishment, but the key measurement you want to make is at the moment that the flame extinguishes. It extinguishes because the agent is sufficient to extinguish it. Then you want to quickly measure the flow rates of fuel, air, and your suppression agent. So I mentioned that you do see a lot of interesting phenomenon before that happens. It's just that they aren't normally reported in the standard. And what you'll see is you start off often with a flame that's yellow and blue. As you increase the agent, the temperature goes down, it actually decreases to the point you can't make soot anymore, and you start to get a blue flame. And then before the flames extinguish, they do all kinds of interesting spiraling, oscillating, opening up type of behavior. And finally, then they extinguish entirely. So there's really one thing that you measure with the cup burner, and that's the conditions at extinguishment. And that gets reported out two different ways, but they're equivalent. If there's the LOI and the MEC. And there's just a simple expression relating them. LOI stands for limiting oxygen index. And the idea with this is that if you drop your oxygen concentration down to about 15% mole fraction, almost nothing will burn. So there's a video here, I'll give the link at the end if you want to see, where someone's actually smoking a cigarette, walks into a room that's at 15% oxygen. Now, they may feel a little bit lightheaded, but of course, you feel lightheaded when you go to Boulder, Colorado as well, and you see that the cigarette extinguishes. So almost all fuels will extinguish when oxygen is depleted to the point of about 15%. And we'll report this then in the cup burner test as the LOI. That's the mole fraction of oxygen at the moment of extinction. And if you know the flow rate of the air and the agent from this last equation, then you can just plug into this simple expression and solve for the oxygen mole fraction at extinguishment, which is the limiting oxygen index. I mentioned that it's also often reported as MEC, so that's on the next slide, minimum extinguishing concentration, but it's basically equivalent. It's just another way of reporting the concentration of your oxygen, concentration of your agent when you have suppression. So usually use LOI for inerts, limiting oxygen index, when you're diluting the air down to 15%, say, oxygen. Or if you have a chemically active agent like halon or the agents shown here, FM100, Novec 1230, then normally you would report out the MEC, minimum extinguishing concentration. So MEC is the mole fraction of the agent at the moment of extinguishment. And if I'll back up a slide here, this is the mole fraction of agent in the flow that goes into the glass beads, into the flow going into the chimney. So we're interested in, within the chimney, what's the oxygen concentration when the flame extinguishes, and what's the agent concentration when the flame extinguishes. So these are shown here on this slide, the MECs for heptane, actually, in this case, for a bunch of these clean agents, and for nitrogen. So what you can see is at the bottom, if you want to put out a fire with nitrogen, you have to put a lot of nitrogen into it, 32% mole fraction, in order to get the oxygen concentration down to about 15%, and the flame will go out. These chemically active agents are much more effective. Look at halon 1301. Unfortunately, it's very bad for the environment, and it's been phased out. You can't make it, you can't sell it anymore. You can use the stockpiles that you have, but it's no longer available commercially. But look at that, at 3.5%. So 10% as much halon as you need of nitrogen will suppress at least a heptane flame and most other flames. So again, if you see someone reporting their results from a cup burner test, sometimes they'll use LOI, sometimes MEC, but if you know either one, you can do the math, the stoichiometry, and calculate the other. If you do this test, and suppose you're selling a clean agent to protect a data server room, what you need to do is run this test for your expected fuel, find out the MEC, and then increase it by 30%. That's the last bullet here on the bottom. Increase it by 30% to have a safety factor. So if you're protecting a data server room, if there's, usually it's a very fast response system. You'll have optical detectors to look for fire. And if it's detected, an alarm goes off. Usually you want to evacuate all personnel. And then a few seconds later, you totally flood the room with 30% higher than these numbers to suppress the flames. Yes?
You might have to. But what are the glass beads? What do you use glass beads for?
Let's go back. So the glass beads help with mixing. You want to make sure that the air is fully mixed with the agent. So they help a little bit with that. But hopefully, if you have a long enough tube, you get fully developed flow, and they should mix before they get to the glass beads. And they also uniformly distribute the flow. So if you didn't have glass beads, you would just have kind of a jet of this air going up, and you could have recirculation and parabolic profiles. You really want a constant velocity, parallel flow going into your flame region.
Did you use glass beads for any reason, or just could be anything else?
Okay. So why do we use glass beads? Well, they're so cheap. You get 1 millimeter glass beads, and now, they're almost free. So they really don't. You could use stainless steel beads. You could use sand. You could use a whole bunch of nuts, fasteners. Anything really that has a small pressure drop to even out the flow. There may also be a plenum under the glass beads. Sometimes you have a screen with the plenum and before you get to the glass beads. Thanks. Good questions.
Excuse me.
Yes.
For the extinguishing, and you measure the flow rates, is there a reason why you're using quartz? Is there the ability to use optical diagnostics to track when the extinguishing happens, simultaneously measured, or is it more of just, okay, I see it and the flow rate just immediately stops because there's no ignition?
Good question. So let me go back to this sketch that shows the quartz. So the question is, why do you need to use quartz? And I think the main answer is because the coefficient of thermal expansion is very low. When it gets hot, it doesn't expand. Therefore, when it gets hot, it doesn't crack. So that's the main reason. But in combustion, lots of times we use quartz windows because it's transparent for UV and infrared. In this case, we're mostly looking at the visible flame. It's blue and yellow. So we turn the lights off, and you can see it very well with your eyes. And we haven't been using anything like a camera to detect extinction or a thermocouple. These also are good ways. So there is good optical access because of this material, but it wasn't chosen for its optical access. It was chosen for the coefficient of thermal expansion. In fact, I believe our chimney broke. And instead of spending $1,000 for a quartz chimney, we bought a $100 BK, borosilicate glass chimney. So I know that our cup is still the quartz, but the chimney is no longer. Thank you. So when you do these tests, you want to make sure that the flame went out because of the agent and that it had plenty of oxygen, that you weren't starving it for oxygen. And so it's important when you do these tests to do the math and check that your flow rate of air was sufficient, that that's not the reason the flame went out. A good rule of thumb we use for fires is that flames like to have about 10 times the stoichiometric air. If you burn in your house a fire in a chimney and you do the measurement, you'll find that the amount of air that gets pulled into that chimney is about 10 times stoichiometric. So that means, when you have a fire, you're usually pulling a lot of cold air from elsewhere in the house. You may be actually cooling down your house and forcing your heating system to work harder. But it's the same for this burner. If you're at 10 times stoichiometric air, then it's considered there's no chance of oxygen starvation. So we always do a calculation to make sure, look at the fuel flow rate and the air flow rate and make sure they're 10 times stoichiometric. So remember that equivalence ratio, phi, is a local property. In a diffusion flame, phi is 1 at the flame. It's above 1 on the rich side, and it's below 1 on the lean side. So phi in the cup burner varies everywhere inside that system. But phi effective is the overall mixed average equivalence ratio called the effective equivalence ratio. So if you consider the flow rate of air and the flow rate of fuel, and you mixed it all up and you calculate the equivalence ratio, that's the effective equivalence ratio. And you want to make sure for these tests that you're below 0.1. You want to have 10 times the stoichiometric air. By the way, when you add nitrogen, or if you add CO2 to the airstream, you're not changing the equivalence ratio at all. The equivalence ratio only looks at the balance between your hydrocarbon fuel and your oxygen. And when you add the agent to the system, you're not supposed to change the flow rate of the fuel or the flow rate of the air. And so we can do the math, and this is what the equivalence ratio math looks like. It's very easy in terms of the cup burner flow rates. You do need to do the calculation. What's the fuel flow rate divided by the air flow rate that's stoichiometric? Here is the last equation. And then divide that into the actual fuel over air flow rates. And you want, again, need to make sure that this is 0.1 or lower. So let me next do a demonstration. And I don't have a hot works permit, but usually if it's for science, universities don't mind too much. So I want to do a little extinction demonstration for you and point out that there are 4 ways that you can suppress a flame. And usually when you suppress a flame, you're acting on 2 or 3, maybe all 4 ways. But if you break it all down, there's really are just 4 ways to suppress a flame. So you can suppress a flame by removing the fuel, removing the oxidizer, right? Flame needs both, by removing enough heat, or by removing the time to, if you have high enough flow rates that the molecules don't reside in the high temperature region long enough, then you can reduce the time and stop the chemical reaction. And this is shown in the fire tetrahedron. You know, all kids are taught about the fire triangle, heat, fuel, and oxygen, but there are really 4 sides of this triangle, with the 4th side being time, or the chemical reaction. So here's just a big lighter. I burn the flame. If I want to remove the fuel, I can remove my thumb off the valve. The fuel's gone, and the flame extinguishes. To remove the oxidizer, you know, I usually bring a shot glass to one of these demonstrations, but I didn't have one today. But if you ignite the flame and hold a cup over it, I think a lot of you have seen this, like a candle in a jar, it consumes all the oxygen. When the oxygen concentration gets down to about 15%, the flame will go out. There's still heat, and there's still fuel, there's still time, but you've actually removed the oxidizer. To remove the heat, this one's pretty easy. You just move your finger across, and even though the fuel's still flowing, there's still air. We've removed heat, and the flame extinguishes. And the last one is like a birthday candle. If this birthday candle's burning and you blow on it, you removed the time. You didn't really remove heat or oxidizer or fuel. So the 4 ways that you can extinguish a flame. And what I want to get across to you is that all extinction events requires at least one of these. No flame will extinguish if you maintain all 4, fuel, oxidizer, heat, and time. And it's one interesting point. I think we all know this. It's very intuitive. But the other thing that I want to point out is that for all flames, for any flame, they weaken. As they weaken, you know, as you remove the fuel, the oxidizer, heat, and the time, the temperature decreases. The peak temperature in the flame decreases. And because its reaction rates are Arrhenius and you increase the temperature, the reaction rate is very steep. If you drop below about 1600 kelvins, then this is the moment when the flame extinguishes. So it seems to be a magic number. If you measure the temperature in this flame, the peak temperature you'll get is probably about 2,000 kelvins. Adiabatic flame temperature is about 2,400, 2,300. But because of radiation, you don't see those temperatures. You see about 2,000 kelvins. But if you drop that temperature by 400 degrees, whether it's by fuel, oxidizer, heat, or time, that flame will extinguish. So what I'll show next is how we can take advantage of that 1,600 degree number and plug it in and see how that works for the cup burner. And by the way, this applies not only to diffusion flames, but to premix flames, all kinds of flames. Happens at a magic number at 1,600. Okay, so there's a hypothesis. This was done by Senecal, but I don't think this is the first person to. They're well known for it, but I think that it was expected before this. And the hypothesis is that if you add an inert to the cup burner, you decrease the peak temperature because, for example, if it's nitrogen or carbon dioxide, it's kind of like throwing sand on a flame. Nitrogen doesn't add any heat to the flame. It can't react, but it sucks heat out because you have to heat up the nitrogen. So if you put in enough nitrogen or CO2 to cool down the flame below 1,600 kelvins, that Arrhenius reaction rate will fall off a cliff and suddenly the flame will extinguish at 1,600 kelvins. Now, of course, it depends a little bit on buoyancy and the residence time, and we've done a lot of experiments with this in microgravity, in drop towers and in the space station. And in microgravity, oddly enough, flames can burn down to 1,100 kelvins. And that's because the residence times are so much longer, they can allow slower chemistry. But even in microgravity, it seems to be a magic universal number. It's 1,100 kelvins in microgravity, 1,600 kelvins in normal gravity. Okay, so the heat release rate here is given by this equation. It's the fuel consumption rate times the heat of combustion, the lower heating value. So next, look at the adiabatic flame temperature. So in the cup burner test, there's not a lot of radiation, but there may be a lot of nitrogen and carbon dioxide flowing into your chimney. And so if you look at the adiabatic flame temperature, it's a reasonable representation of the peak temperature in the flame. As I said, for the butane lighter, there's some radiation, probably drops the temperature of this flame 300 or 400 kelvins. But as you go to lower temperatures, and when you remove soot, as the flame turns blue in the cup burner, you really don't have much radiative losses. So to do a nice, simple back-of-the-envelope calculation of the extinction in the cup burner, what you can do is a hand calculation of the adiabatic flame temperature. And that's shown here. The heat of combustion balances with the temperature increase of the stoichiometry times the specific heat of each molecule. So, of course, any reaction is going to conserve energy. On the left-hand side of this equation, you have heat of the combustion. And on the right-hand side, you have the sensible enthalpy. That's the Cp times the delta T. Now, if you have time and you have resources, you can calculate adiabatic flame temperature with 4, 5 digits of accuracy. It's a thermodynamic parameter, so it's very well known. And there are lots of free software that can do this, like Cantera. And for almost any choice of oxidizer or any choice of fuel, Cantera can give you these temperature predictions. For example, for methane air, 2223. For propane air, 2261 kelvins. But for the cup burner test, it's really not necessary to go to all the difficulty of Cantera calculations, although certainly you could. But you can also do some hand calculations and get pretty close to estimating the inerting concentration, the amount of nitrogen or CO2 that's needed to extinguish, say, a methane flame. And that's demonstrated on this slide, where we do a heat balance at extinction. And so here, instead of using Cantera and doing the full integrals, we say the heat of combustion balances with the sensible enthalpy, and that's summation over the products of stoichiometric coefficient times their specific heat times the heat of combustion. Times the temperature increase. So temperature increase is the adiabatic flame temperature minus 298, and the specific heats, you can look these up in a heat transfer book, are evaluated at some mean temperature. Of course, specific heats increase with temperature, and that's why normally you wouldn't want to take the specific heat out of the integral. But just to do an approximate analysis, we can assume the specific heats are constant and their value at some mean temperature. Okay, as I mentioned, in normal gravity, all flames seem to extinguish if their temperature drops below 1600 kelvins. And so you pick a mean temperature, look in your heat transfer book, and find the specific heats at the mean of 300 and 1600 kelvins, which is 950. And then the heat balance becomes this, where there's really only one unknown in the equation. Heat of combustion divided by that temperature increase of 1300 kelvins now is equal to the sum of the stoichiometry for the products and the amount of agent. So now we have a simple expression, a back-of-envelope calculation with only one unknown in it, which is the agent stoichiometric fraction, nu sub agent. Typically, we assume for a hydrocarbon that you have complete combustion, so you produce only CO2 and H2O. That probably isn't accurate where these flames are about to extinguish. When you cool them down, there's a lot of incomplete combustion. You have carbon monoxide produced, maybe some formaldehyde, unburned hydrocarbons. And if anytime we've run this experiment and opened the chimney into the room, you can smell some unburned hydrocarbons coming out. But it's a reasonable approximation for these purposes just to assume you're making H2O and CO2. However, even at those temperatures, even at 1600 kelvins, these will dissociate a little bit. And in order to account for that, what I'd like to do is increase that 1300 Kelvin temperature increase to 1700, and that gives you slightly higher specific heats. That's a lower denominator, a larger value to divide on the right-hand side and get a reasonable match. And so if you do this calculation, you'll find that even as simple as it is, as approximate as it is, that you get a good prediction of the agent extinguishing concentration, at least for inert agents. Now, I want to talk next about how human physiology and I suppose other animal physiology responds to insufficient oxygen and how that's different from flames. And this is kind of, to me, a key point of understanding that's not so important where in an environment like here where you can't control the pressure, right? Everywhere we go in our lives, we're always at 1 bar pressure unless you climb Mount Everest. But there are environments where that can be controlled, where people go, for example, on submarines and in aircraft, but especially in spacecraft. So I want to get across the two main points here in these two bullets, that human physiology is different from how fires behave. Okay, so in general, most flames will extinguish if you drop the oxygen concentration below 15%. So there are plenty of rooms, there are rare book libraries where they can't afford, and museums where they can't afford to have a fire. So they actually drop the oxygen concentration below 15%, and nothing will burn at that condition. It's still 1 bar, but flames extinguish at oxygen concentrations of 15%. That's the LOI you see in the cup burner. But for people, okay, so flames don't really care about the partial pressure of oxygen. The flame responds to the oxygen concentration. But for people, for human physiology, it's the opposite. Human physiology, we don't really care too much about the oxygen concentration, the mole fraction. What we care about is the partial pressure. And I guess I don't know exactly, I think I understand how it works for flames. It makes sense that if you go up to high pressure flame, you get the same adiabatic flame temperature at high pressure as you do in air, as long as you keep the oxygen concentration the same. Intuitively, to me, that makes sense. I don't know why the hemoglobin and the lungs work the way they do for people, but human physiology responds to the partial pressure of oxygen. So at 1 atmosphere, it's about the same. Flames don't feel so great below 15%. Humans start to feel lightheaded below 15%. So the partial pressure of oxygen in both cases at 1 atmosphere is the same. But if you go to other atmospheres like spacecraft and submarines, then things start to behave differently. The flames respond differently than the people. And that's shown on this next slide in terms of spacecraft. And I worked for 9 years at NASA Glenn, so there was a lot of interest there, a lot of discussion about making spacecraft safe. And they're still, that's their number one concern. What do we need to do to make spacecraft safe? And they have a horrible example of how to do it where they're not safe. And this was with Apollo 1. And this is back in the 60s. And they said, you know what, if we run 100% oxygen, but at 1/3 of a bar, 1/3 of an atmosphere, the crew will feel fine. So now instead of breathing 21% oxygen, it feels like they're breathing 34% oxygen. They probably actually feel a little bit more energized. So, you know, they have clinics now where you can go breathe oxygen. It makes you feel real sharp for a while. So the crew were okay. They weren't lightheaded. They felt fine. And the spacecraft, it could be 1/3 the mass. So you have 1/3 the pressure in orbit or going to the moon. Well, of course, the designers love that. It probably weighs 1/3 as much. But the fires, they don't care about the partial pressure. They only care about the oxygen concentration. The fires, 100% oxygen, of course, that's a huge fire hazard. And I think NASA was aware of it. You know, they had to make trade-offs in safety, but as a result of that trade-off, they lost 3 crew members. They burned on the ground. They think it burned so fast they couldn't really investigate the fire very well, but they think that in Florida, a wire overheated and didn't have to heat up that much, but in 100% oxygen, even at the reduced pressure, it erupted into flame and everything burned so fast. The door also opened in, so everyone on the outside was pushing to open the door. The 3 astronauts were pulling on the door. They couldn't open it because the pressure increased and they all perished. So after that, NASA learned their lesson, but they still are trying to push the limits a little bit and not accepting what the fire scientists like me say is, you know, you have to accept the weight penalty of having a heavy structure, and you should fly at 21% oxygen. You can put whatever pressure you want in there, but as soon as you enrich the oxygen beyond 21%, you're also increasing the flammability. Okay, after that fire, Apollo made the door open out and they dropped to 50% oxygen, but it was still very hazardous. And for me, if someone offers me a scuba tank and says, hey, we want you to walk into a methane room, it's full of methane, I'll be pretty scared. You know, I don't really want to have that experiment. But if they offered me the same thing and said, walk in a room full of oxygen, then I think I would have to say no. So going into a room of methane with the right breathing apparatus has got to be safer than going into a room of oxygen. In pure oxygen, everything is a fuel. Your hair, your skin, your clothes, everything's a fuel. So now on the International Space Station, they went back to Earth environment 21%, 1 bar. As they're building out the new spacecraft for lunar and Mars exploration, the next generation is called NASA Orion. And some of them are using 21% oxygen at 1 bar, but some are now pushing it up to 26% oxygen. NASA does like going to higher oxygen because it's less pre-breathing time for the astronauts who are going on spacewalks. By the way, at the last bullet there, the Artemis spacesuits are going to have 100% oxygen at 0.3 bars. So if your spacesuit is at 1 bar full atmospheric pressure, you're so stiff like the Michelin man, you can't move. So they had to decrease the pressure, and they go to pure oxygen. But this is a very hazardous environment for them. And then the lunar habitats now, they're pushing it up to 34%. My former boss at NASA, Glenn, he told me last month that he thinks that crew members, anybody going in this environment, should be required to shave their head. That hair is flammable enough, and why would you want to take the risk that you're going in 34% oxygen or, you know, heaven forbid, 100% oxygen? Why would you want to bring that much fine fuel into that environment? He also told me that no one really knows how flammable hair is, and I guess if you don't know, he would rather err on the side of caution. But he's a manager at NASA, and you know there are other concerns that have overweighed his decision on that, his recommendation. This is the video I mentioned before, FirePass. It's a 4-minute video. It's kind of old now, but it's kind of funny. They have a room at, I think, 15% oxygen. They pass a candle in, it goes out. They pass a cigarette through, and nothing will burn at those concentrations. Okay, with that, I want to talk about the second standard test for this hour, and this is a test where you can burn liquids. So we're starting to transition. Again, most combustion scientists are interested in burning gases or atomized liquids, and a few are burning solids like coal. But most people in fire are looking at condensed fuels, either liquids or solids. So this is a bit of a transition from the gases to the liquids. And this tester here that you can see is called a Cleveland open cup tester. It was invented in Cleveland, And the way it works is that it just plugs into the wall, 110 volts AC, and there's a knob on the bottom. It goes from 0 to 100. It's basically a variac, and it controls the temperature of a heater. So under there, there's an electric heater. And then up on top, you can see a brass cup. And brass is good because it has high thermal conductivity. And the idea is that this cup is isothermal. And inside the cup, you pour your liquid. And it can be something like motor oil or alcohol, something with a relatively high boiling point. We use thermocouples to measure the temperature inside the liquid because it's so much easier, but the standard test actually has a long mercury thermometer that hangs down that can hinge in and out of the pool, but you want to make sure that you know your pool temperature. And then on the front here, with this black handle with the brass tube, is actually a flame that you pass over the cup. So you can see feeding into the bottom of that handle, there's a barb fitting. You can slide a flex hose over it and provide methane or propane as your flame. So what you do is you watch the temperature of the pool and you swing this tube over it so that the flame goes across back and forth, and you watch and watch. Initially you have no ignition, and as the temperature increases, eventually the pool ignites, and this is the flash point. And it's a really important parameter to understand for transportation safety, for fuel safety, because some fuels, you can't ignite them at room temperature. We burn a lot of diesel in our experiments, and we can either call up environmental safety, they'll take it away and pay someone to take care of it, or since we have a big exhaust hood, usually we'll just go burn it off. And when you pour diesel into a pie pit plate and you hold a fire to it, a torch, it won't ignite. You cannot ignite diesel. Now, gasoline's the opposite. You don't want to really do this with the gasoline because you get a fireball. But diesel's hard to ignite, and so diesel would be an ideal thing to test with this, but it also tells you about the transportation safety, that on a lot of work sites, diesel trucks are allowed, whereas gasoline trucks aren't allowed. So the flash point, the minimum temperature for which a liquid fuel can burn, is an important safety parameter to understand, and it's a property of the fuel. So this is called the Cleveland Open Cup. It's the ASTM D92 standard, and it simulates the ignition of a liquid spill. So it is a fully open cup. I'll show a little bit later some that are closed, where the cup is enclosed. And it's good for liquid fuels with high flash points, things like motor oil, even tar, candle wax, and so on. And you can measure both the flash point and the fire point. I'll talk about that in a minute. It has a recommended temperature range for the fire points of 79 to 400 degrees C. It uses a 70 millimeter specimen, and you heat it at about 5 degrees per second, so 5 degrees per minute. And the pilot flame is 5 millimeters, about 2 millimeters above the cup. And you'll see in my slides, and by the way, if you're trying to follow on your computer, all these slides are there, but I've reorganized and moved them around, and I'm sorry for those of you following. I checked with Chelsea, and she said that this afternoon, if I give her the new PowerPoint, she'll replace the one that's there. So, but if you're interested and you want to play back these videos, this is a 3-minute video that shows the Cleveland Open Cup in action. And especially, I think there are probably people here who come from small schools that don't have a combustion course, where some of these materials may be very helpful for you when it comes time for you to teach your combustion classes. Okay, so this is what the open cup ignition test looks like. And you start in the condition at the left, where the liquid is cool, and you slowly heat it. And as you're heating it slowly, you pass the pilot flame across and see if it ignites. So, for example, on the image at the left, suppose you have motor oil at room temperature. It's very slowly evaporating, but if you pass the pilot flame over it, it's like me with the diesel in the lab. You can't ignite it with the torch. And slowly increase the temperature, and you turn off the lights. You want to have your eyes dark adapted because some of these flames are very weak and blue. And at some point, you see a flame that starts where you have your pilot and propagates across the pool and goes out. And so this is called the flash point. It's the lowest temperature at which a temporary flame, an intermittent flame, can be supported on that pool. And then if you go just a little bit hotter, usually it's only 1 or 2 degrees, and you pass your pilot flame over, now you get a continuously burning flame. And at that point, you snuff it out. You just take a pie plate and you snuff out the flame, cool it down, and you can repeat the test. So this is how the open cup ignition test works. And it's usually very accurate. Usually, as you do repeats, you're within 1 or 2 degrees of the measurement. You do it a few times and take an average. So here's some factoids about liquid ignition limits. The flash point is defined as the lowest temperature for a temporary flame, intermittent flame, and the fire point is the lowest point for which you can have a continuously burning flame. A lot of times in combustion we talk about the AIT, auto ignition temperature, but this is a completely different test. It's a test kind of in a thermos. You drip a few drops of your liquid in, like gasoline with air, and you heat it up until you see fire shooting out the top. Auto ignition is a much higher temperature and an entirely different test. There's no pilot in an auto ignition temperature test. But both of them are measures of ignitability of liquids. They're both important to understand how those fuels burn and the fire safety. And their fundamental properties, which is to say that the results shouldn't depend on the test you do or who's doing the tests. These tests go back to the 1800s when there were lots of liquid fuel fires as a way of standardizing the test in order to have standard rules for how you transport these liquid fuels. Okay, this test uses an open flame because really it's the strongest ignition source. I'll show some other tests tomorrow, later today, sorry, that use a spark igniter or a hot wire igniter, and those are never quite as viable. An open flame, because it has the temperature and the radical concentrations and some buoyancy going on, usually an open flame is the strongest ignition source you can have. As a caveat, the last bullet here is that some fuels can misbehave in this tester. For example, you can use it to test the ignition point of wine. And there have been some famous fires where it was claimed that wine burned. Certainly whiskey, and there was a lake that whiskey leaked into and caught fire and caused a fire tornado. So some alcohols can burn. Wine, you can actually measure the fire point of wine, but it's a little tricky because as soon as you heat it up, you have preferential vaporization, the alcohol is leaking out, and so the test isn't that repeatable. So you can have preferential vaporization, which makes wine or beer difficult to test. And you can also have water condensation. For example, if you do this test with methanol, water can condense from the air on a humid day into the methanol and dilute the methanol and change the fire point. But also, as soon as you ignite a flame on that methanol, it's producing H2O, and H2O is likely to diffuse to the surface, which is cooler, and condense into the liquid. Now, you're not going to have condensation if you burn an oil. So motor oil or heptane, you can sit it out all day in a humid room and it's not going to absorb any water, but the alcohols do. So you need to be a little bit careful if you're testing methanol, things that are miscible with water, or things that allow preferential diffusion like beer or wine. My students would love to test beer and wine, and I just haven't had the nerve to try it yet. So if you do these tests, they can be very important to guiding the transportation. So these are the transportation classes, U.S. Department of Transportation. It's funny because the numbers here, as they increase from 1, 2, and 3, the fuel becomes less flammable, whereas for the refrigerants, if you remember yesterday, going from 1 to 2 to 3, they became more flammable. I don't know what's the rationale for doing that, but these are old classifications that won't be able to change. So this is from NFPA 30. It's by a slightly different test I'll show in a minute, closed cup test. But we have classes 1A, B, C, 2, 3A, and 3B. And U.S. Department of Transportation, they've drawn a line here between 2 and 3. And they say if you're transporting anything that's more flammable than, say, canola oil, that you have to take special precautions. So what's shown here is the flash point temperatures down around 22 for some things like gasoline, super flammable, and ethanol a little bit less. Diesel, if you want diesel to burn, there's a broad range because diesel isn't a monomer. There's no molecule called diesel, but somewhere between 40 and 60 degrees is the temperature you need for diesel. And that's why in my laboratory at 25 degrees C, even with the blowtorch, I wasn't able to ignite a pool of diesel. So not only it's an interesting test, I like it because you can do hand calculations and learn about the thermodynamics of this, but it does have a true application for transportation safety. So I did a little analysis here to look at the flash points as a function of the boiling points and found tremendously good correlation is R squared of 0.94. So this is for hundreds of published, well, I don't know, maybe 100 published flash points. On the y-axis is the temperature at the flash point versus their known boiling points. And so you get a really excellent correlation. If ever you have a fuel for which you can't look up the flash point, all you really need is this equation and knowledge of their boiling point, and you should be able to predict quite easily the flash point. The key takeaway here is that something that has a high boiling point, like motor oil, is going to need to be heated close to that boiling point to ignite. And something that has a very low boiling point, like gasoline, will ignite at room temperature. So this method does give you a way of measuring an approximate lean flammability limit. Now, normally if you want to measure the LFL, you get a bomb. You get this half-liter, very heavy, usually a solid piece of stainless steel that's machined out on the inside. And you do partial pressure mixing. You put in your fuel and your air near the flammability limit. You spark it. You have a high-speed camera if you have a window, or a high-speed pressure transducer. And this is the best way to measure lean flammability limits. Or if it's a refrigerant, then you can use the AST E681 standard that I talked about yesterday. So there are better ways to measure a lean flammability limit, but it turns out that the Cleveland Open Cup is a good way of approximating it. And the way it works is that if you consider the height above your pool here on the y-axis versus the concentration of your fuel in the gas phase, of course, the higher you go above the pool surface, the lower is the concentration of fuel because it's diffusing away. And at the moment of ignition, at that fire point, right just when you're barely hot enough to ignite, there's only one place that's rich enough for it to ignite. It's right on the fuel surface, and the concentration looks like this. So at the fire point, the concentration of your fuel just above the liquid surface is at the lower flammability limit. So if you measure the fire point or the flash point, either one, then you can estimate the lean flammability limit from this method. And so I'll talk about that in the next few slides. Okay, so imagine you're working with gasoline. And initially, suppose you're all the way to the right here. It's really cold. So it's in northern Canada or northern Alaska. If you spill gasoline on an outdoor surface and try to ignite it, it's going to behave just like the diesel. It won't ignite. It's so cold that it's barely evaporating at all, and the concentration above the pool surface is below the lean flammability limit. So on the plot at the right, gasoline at minus 50 degrees C, you can't ignite it, even with the blowtorch. Now, at the other extreme, gasoline at 25 degrees C, this is the condition you have today. If you poured small bit of gasoline on the sidewalk and held this lighter up to it, it'll erupt into flames. So at that condition, very close to the pool, you're above the upper flammability limit. There's too much gasoline. Gasoline evaporates very quickly. So if you go too close to a gasoline pool at room temperature, it's too rich to burn. But if you move a few millimeters above the pool, that concentration decreases, you pass the upper flammability limit, and you have that region that I shaded there where ignition is possible. And then if you go, say, 100 millimeters above the pool, it's too lean to ignite. But at 0 degrees C in gasoline, you can have an ignition possible close to the surface and out to some other distance. So this is kind of, in a couple of sketches, what the cup burner test is doing, changing the temperature and moving the concentrations around to pass the lower flammability limit and upper flammability limit. By the way, in a gasoline tank in your car, in steady state, that gasoline is constantly evaporating, and you're actually, at a day like today that's warm enough, you're well above the upper flammability limit in your gas tank. So in the movies, don't believe it when you see, I think it was No Home for Old Man. Or there are movies where people open the gas tank and throw a match in and it explodes. And that may be possible under certain conditions, but in general, in steady state, there's too much gasoline in that tank and nothing will burn. So ironically, gasoline, it evaporates so fast that in a sealed tank, it's actually probably more safe than diesel would be. Okay, so in order to do this analysis, a rough conversion from the fire point and the flash point temperature to an estimate of the lean flammability limit, you need to incorporate the Clausius-Clapeyron equation. And I think a lot of combustion scientists, you don't work much with Clausius-Clapeyron because you're working with gases. But in fires, when fire research, we do a lot of work with Clausius-Clapeyron. So it goes back to your thermodynamics days. And basically, it looks at a steady state condition where you have temperature of a liquid pool, as shown here, just in a Petri dish. And in steady state, you want to know what's the mole fraction above the pool. In fact, even when you have an open pool, like a fuel spill, if you go close enough to the liquid surface, you'll be at the saturation condition. So 1 nanometer above a liquid, even if it's not a steady condition, you will have the Clausius-Clapeyron condition apply such that you're at the vapor pressure for that temperature. Okay, so this is the differential equation for Clausius-Clapeyron, and it's an exact solution. It's been around for a couple hundred years. It's a differential equation. The change of partial pressure with respect to temperature, that derivative, is equal to the enthalpy of vaporization, that's HFG, times molar mass, divided by universal gas constant, times the pressure, divided by temperature squared. So the parameters are shown there. It's a differential equation. But if you have a computer, you can solve this exactly, and you can find, for what you basically want to know is, for a given temperature, what's the partial pressure of that saturated fuel. But we can approximate this and integrate separate variables, as I'll do on the next slide. First, let me show, though, a phase diagram. Phase diagrams exist for lots of different liquids. For example, this is the phase diagram for pentane, and it's a plot of temperature versus the partial pressure. And that blue line, you can see there's a liquid phase and a gaseous phase, but the blue line is the saturated liquid condition. And so for any temperature, for example, if you look at the x-axis at 100 degrees C, you can read up and find that the partial pressure of pentane will be about 10 bars absolute. So that blue curve is the partial pressure of a liquid in saturated conditions in steady state. And the beautiful thing about the Clausius-Clapeyron equation is that it is an equation of that blue curve. It's an exact equation. So we can estimate the lean flammability limit from the flash point as follows. We're going to take Clausius-Clapeyron and separate variables and take the HFG out of the integral. It's not that precise because the enthalpy of vaporization decreases as temperature goes up. But then we can find that the partial pressures on the left-hand side ratio in logarithm is about equal to the enthalpy of vaporization times the difference of the inverse temperatures. Now, for lots of fuels, we don't have all these, you don't know the partial pressures at all the temperatures that you would want. And so, but almost all fuels will give you the boiling point. So if you know the boiling point, you specify that as one of these temperatures. And of course, at the boiling point, the saturation partial pressure is 1 bar. And so if you plug that into that equation, we have another approximate equation, but it's not too bad, which relates the mole fraction at saturated conditions to the temperature. So that's the final equation there where it says natural log of x is approximately equal to this quantity. So if you know the boiling point and you know the fire point, you put in the fire point in as your temperature there, then everything else should come out quite easily, and you can find the mole fraction of that liquid just above the surface. And as the takeaway here, the last sentence, if the T now is the measured flash point, then this is a good way of estimating the lean flammability limit. as your mole fraction. Now, normally when you look at mixtures, okay, if you're mixing two different fuels, suppose you're mixing gasoline and diesel, then you can make a plot of the x-axis being the mole fraction, right? Where you all the way on the left you have compound 1, maybe your gasoline. All the way on the right you have compound 2. And you'd kind of expect a linear behavior between these two, between the fire points. You'd expect, if you're at a 50-50 mixture, that the fire point would be about halfway between the fire points of the two components. And that generally holds, that's Raoult's law, that the vapor pressure equals the vapor pressure times its mole fraction in the liquid. And usually that works. But what's been discovered lately, and this is a brand new paper in Progress in Energy and Combustion Science, is they've been looking at some extreme fire points. And it turns out that in some cases, that it's not conservative enough. If you know the fire points of two compounds in a liquid, the fire point can actually be, the true fire point can be actually lower than either one of them. And so it's an interesting topic. They call these extreme fire points. The curvature can either be up, as in the upper plot, the green, which means the mixture has a higher fire point, it's safer, or what could be worse is where the curvature is downward in this red case below. So in the red case, you can see that for any mixture, almost any mixture of the two compounds, the fire point is lower than the fire point of either of the compounds by itself. So it's just a caveat. I think what it says is that if you're looking at a mixture, applying these mixture rules is rather risky, and you probably should test the exact mixture in your fire point tester. Okay, so that was the open cup test, the Cleveland open cup test. It's nice for students. It's nice for me because you can see the fire. I really like seeing the fire, seeing the colors. The open cup, the cup burner test is a nice test that I started with where you can see the flames. The open cup test you can. But a lot of times people prefer the closed cup test because it gives you a slightly lower temperature. It's a little more conservative. So it simulates ignition more like not so much on a spill, but in a container. If you have a gasoline container, you fill it up at the service station. This simulates the closed cup burning test. Industry prefers the extra safety margin, but it can't measure the fire point. And there are a few of them. On the next slide, I'll show the most famous one. It's the Penske-Martins, but there's one called Setaflash. They have nice names, Taglia Blue, Closed Cup Tester. So these testers, they look more modern, certainly are more expensive, but not necessarily more accurate or more interesting to look at when you want to see the flames. And so this is then the Penske-Martins closed cup. It's a different ASTM standard and it gives results that are a couple degrees cooler. The way it works is you put your liquid inside a cup of a similar size to what I showed, and then you have a pilot flame that passes above the liquid. It's closed, but it has some vents, so it's not completely sealed. And then if there's a flame, of course, the flame will be at the flash point and it will extinguish. You can't measure the fire point. It's recommended for high viscosity liquids and temperatures above 30 degrees. But some of them, like this one that's shown here, are fully automated. Basically, all you do is you pour your liquid in, you push the start button, like brewing a coffee, and it slowly increases the temperature. It detects the flames with, I think, optic methods, and passes the pilot light, and then reads out to 3 digits, what's your fire point. So, what's your flash point. So this is a closed cup test. I guess, it's interesting that we have open cup test, closed cup test, and some are preferred for some are required for some transportation regulations, and some for others.